Alright, so in this one we're going to look into rendering the whole scene. So I have prepared some code, here it is, and I'm just going to tell you what it does. First, we're just going to look at it, and then we're going to dive into details. So actually, I have adapted this code from the repo that I have. So Ghostface colab, that's my nick, and VSLAM. And then in the sim folder, there's like egocentric rendering, scene rendering code. And yeah, here's the repo, and I built VSLAM on top of this. So in this way, I control fully the environment. I can do whatever I want there. It's kind of not like production ready, it's more like academic, but still. And here I have ported it to colab, such that it's like easier for you to use. You don't have to install anything or whatever, you just like execute it. So yeah, let's execute it whole actually. Let me restart the environment just to make sure that it all works. And then yeah, we'll just wait a little bit and see how it executes. Okay, so it executed all the imports and definitions, and now it's in this rendering code. It's low-key slow, such is life. So in the meantime, so this code introduces a bunch of intermediate steps. I'm not going to be able to explain everything. Anyway, so here's the scene. So it has a bunch of triangles. It has ground and sky. And yeah, let's just like render, play around with the scene a little bit. So maybe let's reduce it first. Let's just have a triangle that's like a scene that has only 2 triangles. Alright, 2 triangles. And then let's change the camera pose. Let's introduce yaw. That's so yaw was this. Let's do 0.2 or something. Okay, so we're rotating a bit. What if we rotate some more? 0.7. Yeah, we rotate some more. What if we okay, rotate it back, and then we go up a little bit. Don't really see a difference, right? So yeah, let's do this and compare carefully. And then this again, so go up a bit and rotate a bit. Okay, looks a bit different. Notice where the horizon line is. Go up some more, like maybe by 1 meter. That's quite a bit higher. Yeah. Yeah, and that's how it works. So you can just play around with it. I will share the link to the code. So let's work here, maybe. Let's do this. And like rotate everything to the left. 5 seconds to render something. Right, yeah, that's too much of rotation. Like, it's maybe let's do like 0.2. And at this point, I'm just like playing with numbers. Anyway, now it's more like understandable what has happened. Cool. So let's look into details. So okay, here's like a bunch of code that defines scenes. This is the main function, render scene pixel-wise depth. So, and this in the repo, that's like sim egocentric render. This is where that's the entry point, render scene pixel-wise depth. All right, so we take camera pose, it's SC3 pose, then triangles. This is structured object, the main, so it has like points, and this is just like coordinates of the 3 points that define the triangle, and then faces, so face color, like front face color, back face color. So triangle just has a color. Calm intrinsics, you should know what that is. We talked about it in the previous lecture. And then we have color of the sky and color of the ground. And we have clipping surfaces, which is not something that we talked about. And I'm just going to explain it real quick right now. So really it's part of the camera intrinsics, I would say. So, all right, so here's the observer, bird's eye view, and here's so at Z, so the coordinates are always like this. Z points out, and at Z equals 1, there's the frame, the picture frame, and then here's the objects we're observing, and let's have an object to the side, and here let's have an object like in the middle. And then if I so here's the very edge of the what is visible on the picture, right? So just like from the first person perspective, right, it will be something like this. So this one over here is, I don't know, it's like here or something. This one over here is like, I don't know, here. And then this one, right? So what if it's, so wait, actually this one, right? I mean, it would be here somewhere, right? But like we just don't see it at all. So that's kind of easy, right? We can just compute the coordinates of those, right? And just see, okay, that's like just too far out. But what do we do? What do we do with something that would like fall somewhere in between? That's like partially visible right here. So we see like an edge of it, right? So like the fully it would be something like this, but we just see like a small piece of it, right? So this whole idea of clipping surfaces, there's like 4 planes, 4 like half planes that really bisect those lines. Oh no, sorry. Yeah, here it is. Okay, there's like 4 half planes that they all start in the optical center of the camera, and there they all go right through those edges of the image, right? And then when we just basically compute an intersection of the triangle, right? And this half plane, and then because it's a triangle, it can so either we don't cut it at all, or we cut it into this one, so like we just create one triangle from it, or we cut it into this like the second thing over here, right? And then really what it means is like we cut it into 2 additional new triangles. So here's like triangle number 1, this one over here, and then here's like triangle number 2, right? So 3 things that can happen. We just don't cut it, we don't see it at all, or we cut it into 1 new visible triangle, or we cut it into 2 visible triangles. And those clipping surfaces are those like half planes that do the cutting, and then there's a bunch of code that resolves the cutting. So this is just clip triangles, and I just took it from a website. You should check out this website. There's like a link to the code. So they just explain it in detail, and they provide some sample implementation. I think it was like in pseudocode or CVP. I just ported it to Python. But yeah, more or less that's what it does, right? So we just take a triangle cam points, and then we have some like front colors, back colors, and those clipping surfaces. And clipping surfaces are completely a function of camera intrinsics. And then we define new triangles. And because each triangle actually can be cut into 2 additional triangles, in this corner case that you have seen just a second ago, this triangle cam points can be actually bigger. So it can be up to twice the size of those triangles. So yeah, just something to keep in mind. So then we take, oh, and here's an interesting thing, right? So we're going to do this like parallel Z buffer render algorithm. And yeah, so what the hell this means? So let me go to the lecture mode again. I hope I can explain it live well. Let me see. Okay, so So we have a bunch of triangles that we want to render, right? And so here's the triangle, right? So this is kind of easy because like the triangles don't really overlap, so we know what to, like we know exactly what color this pixel should be, or this pixel should be, or this pixel should be, right? It's exactly the color of the triangle, right? I mean, we're ignoring shading and so on. We could also have shading, and then it's like some kind of function of depth. But like, what if our triangles overlap, right? Like this. So then we need to resolve, for each of the pixels, we need to resolve which triangle is front. So is this triangle A front, or is this triangle B front? And if for this pixel the triangle A is front, then of course we paint the color of the A triangle. This pixel should be the color of A triangle, and otherwise it should be the color of B triangle. So how do we solve this? So the actual rendering code, like in the modern graphic cards and whatnot, it solves it in a different way, slightly different variant of the way that I solved it. I did it in this way, just to use jacks, really. So that's kind of not the recommended. Like if I were writing production code, this is not how I would do it, but still this is how I chose to do it for this particular one, because I'm focusing on VSLAM, and because it's just literally how I wrote it. So usually what you have is like you have Z buffer, right? So on the top of having just normal, like pixel array, you have a Z buffer, and the Z buffer basically tells you, so you iterate over all triangles, and for each triangle, so let's say we find this triangle, and then for each pixel we remember so not only the color of the pixel, which is like the usual RGB, so 0 to 255, right, the uint 8, but also we remember the depth, a float depth, at what depth this pixel, at what depth is the point of triangle that painted this pixel, right? So let's say we first paint the triangle A, right? So let's just paint the A, right? Here's like this grid of pixels, right? There's really many of them, and then let's say, and like let's just zoom in, right? So we have this grid. I'm just zooming in this thing that I have drawn here. So we say, okay, A is orange, let's say orange, and then B is green. So for A, first we're painting A, and we say, okay, so this is orange, and then at depth, let's say 5, and then this one to the right is also orange, at depth maybe like 5.2, because like it's slightly, like let's say this is deeper, and this is more like to the front of us. So those are deeper, and this is to the front, because it's just like slightly slanted. And then this one is kind of like similar depth, but slightly deeper, right? So orange, 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 right? Let's say we have finished this. So okay, A is rendered, and then we go and render B. And then for each of those, we would compare, right? And maybe like B is kind of opposite, right? So this is more like to the front, and this is like deeper. And we could choose numbers such that they sort of overlap, right? And like one like intersects the other. So we would compare, okay, so if I were to render B here, right, what depth would it be? And if it's in front, let's say that's like 4.8 or something, then we would literally say, okay, so instead of 5, now we have 4.8, and color of B 4.8, and the color of B was green. So now it's green instead of orange. And then we go to this one, and then we go to this one, and like one by one we compare. And this is literally the Z buffer, right? So Z buffer is this idea of remembering depth, right? And then so usually how it's done, it's like you just do it for all like you iterate over triangles, and like maybe you can do it in parallel, but like you just remember, you just hold the z in place, right? Because like if you had, I don't know, 50,000 triangles, right? Like obviously you cannot compute the z buffer exhaustively for all of 50k, because that would be huge, right? That would be like, I don't know, what's the resolution of the screen? Let's even take this 1000 by 800 resolution of the screen, right? So this times like 50,000 triangles, that's a gigabytes of memory. So you cannot possibly do this. But that's in production, right? But like because I have only a few triangles, maybe like on the order of max of 100, it's still kind of a lot of memory, but I just exhaustively compute the z buffer for each of those, and then I flatten them out at the end, which is memory consuming but fast in JAX. So that's what I do. So yeah, that's kind of what this parallel z buffer means. But you can see all of those computations are okay. So just coming back, right? So where's my mouse? Here's my mouse. So render scene pixel wise. I take camera pose. I take triangles. I extract the coordinates of the points from the triangles. I transform them from the word coordinate system to the camera coordinate system, and here I have them in the camera, and then I clip them. So maybe I transform the triangles into some new triangles that are clipped and that are guaranteed to be inside this screen right now. And then oh yeah, exactly. Okay, and then I do the projection. So if I were to project them just into image coordinates, right, I will then translate them to pixels. And then I have depths. So I just have these two separate arrays just for the convenience of this parallel z buffer render. And then I go into the parallel z buffer render. And then let's come back to this parallel z buffer. So there's one more detail I want to share how I do this. And again, be mindful that this is sort of not the, like if I were writing production rendering code, that's definitely not how I would write it, but that's what I did just for fun and just for my own understanding. So if I have a triangle, right, there's this concept of barycentric, check out my nice writing, barycentric coordinates, and that's basically a way of figuring out, so this point, right, if I were to express it as a linear combination of those 2 points, like a, b, c, right, what is it, right? So this point over here is just like 100%. It's like 1 times b plus 0 times a plus 0 times c, right? And then this is 100% c, this is 100% a, right? So that's clear. And then for each point I can inside the triangle, and actually kind of also outside the triangle, but never mind this. For each point inside the triangle, right, this one and this one and this one, I can express it as a linear combination of a, b, and c, right? So if I have the depths associated with a, b, and c, I can easily compute the depth of this point, right? Because I just have the depth of a, and I have the depth of b, and I have the depth of c. So it's easy to compute if I have barycentric coordinates, it's easy for me to compute the depth of a given point. So what I do is, like, for each triangle in the picture that I want to render, I express so I take centers of every single pixel in the image, and I express it as in barycentric coordinates of the triangle, right? So here's a pixel, I express it in barycentric coordinates. Here's a pixel, I express it. Here's a pixel, I express it, right? So I say this is like tiny bit of this, and like sort of 50% of this and 50% of this for this given pixel. And for this one, it's kind of more of this, right? And less of this, and so on and so forth, right? So, and then based on this, for each pixel, I have also associated depth with it. And then I say Okay, ignore all the pixels outside of the triangle, right? Let's take only the pixels inside the triangle, and then for each I have depth, and then I sort of take arc. So I do this for each triangle, right? So here's like this array for triangle 1, and here's the same thing for triangle 2, and then here's another thing for triangle 3, and then here's another for triangle 4, and so on and so forth, right? And then so here's like this, right? And then like for this one's probably somewhere like here, right? And so on and so forth. And then I take like arcmax of each pixel's depth, right? Arcmax of each pixel's depth. And then I see for this pixel over here, arcmax is 1. For this pixel over here, the arcmax of depth is this. And then for third one, actually it should be like arcmin, but never mind, right? It doesn't matter, it's just like coordinate flip. Yeah, let's do like arcmin. I take arcmin. So for this one, for this pixel, arcmin is 1, and then for this one, arcmin is 2. And then based on this, I know which color this given pixel should be, right? And like if it doesn't intersect any triangle, then the depth will be like plus infinity, right? And then I can just compute, okay, does it like fall beneath the horizon, because then it should be the ground color, or like above the horizon, in which case the it should be the sky color. So that's how I render those things, right? So yeah, you can see here's exactly what we do. Where's my mouse? Okay, here it is. So I compute for every single pixel in the image, I compute, and for every single triangle in the image, I compute the barycentric coordinates of the pixels in each triangle, right? And then we compute depth of each pixel per triangle, and then I only take the pixels that are inside the triangle, and also only take the, so I don't want to render stuff that is like beneath us, behind us, right? So I only take stuff that like can be seen by in the image plane. And then yeah, here's my argmin, and here's literally the color. So I take the argmin and the index of the color, and that's my image. So yeah, that's how we do rendering in this like most naive way. If you were to do like shaders and so on, right, you would want to blend those colors based on how the lightning falls on the triangle, right? And then you would start doing all these tricks. But yeah, this is how I do it for now. So yeah, just computing barycentric coordinates from the pixels. I literally just took it from Wikipedia. And yeah, a bunch of math, so getting 3D poses, getting rotations, we discussed all of this. Yeah, clipping, you can read about it on this dude's website. Thank you so much, Gabriel. That was pretty cool. Yeah. And a bunch of colors. And yeah, you can see I sort of wrote it with a lot of boilerplate, and that's how I'm like, it's kind of like habit from work. Just everything becomes this like algebraic data type. I really like this attribute classes, but yeah, it's all just like boilerplate. You could lose some of the understandability and readability of the code and just like shorten it significantly by just not having all the structure types and just like operating with raw numbers, which would make it like we could drastically shorten all this code, and that in some way makes it more understandable. That for me, this benefit of like knowing, oh, this thing over here, right, it's like it has some semantic meaning, it's meant to be points in the camera coordinates, right? Actually, it's even best to have doubling up of this information for me, both in the name and in the type, right? Which in the end, this type is just like an empty array. But because I give this alias like semantically meaningful name, for me it makes it easier to read. It's for sure more verbose, but yeah, that's how I prefer it in practice. But yeah, it's a matter of taste ultimately. I wouldn't mind seeing code that's the opposite. Yeah, and that's pretty much it. So in here, right, in the repo, I made something called wait, what was it? Actor simulation. Yeah. So this actor simulation is basically like a way to wait a second. Maybe I can try running it. I'm not sure if it will work like straight away. Yeah. Let me see. Like this, and like if I just run it, like if I do manual equals true, and then save recording equals false, and I just run it, then what happens? Let's see. Right, doesn't work. Why? Yeah. Alright, never mind. That's impossible. But yeah, anyway, what I do, probably I just moved around some stuff. What I do in here is I just I just have some pre-recorded sequence of motions, and then I render each separate step of this. I just like, we just keep moving the observer, and then we just oh yeah, I know how to show it. Yeah, so we do exactly this, right? So there's like some kind of like pre-recorded route, and I just run the simulation of like what does the robot see, right? And here's like you see this recording of what the robot sees. And yeah, then we just save it, and we're going to do the actual VSLAM on top of this. Cool, and that's the next lecture.